Con estas actividades iniciamos nuestro segundo día del 15 Congreso Internacional Tendencias Tecnológicas en Computación, organizado por el Centro de Innovación y Desarrollo Tecnológico en Cómputo. Bienvenidos. Agradecemos ampliamente el apoyo de el CGFIE y la UPCE por prestarnos el auditorio, por recibirnos. Es un gusto estar en este auditorio. Y pues les damos la bienvenida a este segundo día de actividades. Vamos a continuar con el Congreso para ello le voy a ceder ahorita la palabra al doctor Eduardo Vega, que es Chair del Congreso. Doctor, si es tan amable.
Buenos días a todos. Como ya mencionó el doctor Itzama, continuamos con las actividades de la edición 15 del Congreso Internacional Tendencias Tecnológicas en Computación. El día de hoy tenemos planeadas dos pláticas aquí. La primera de ellas que voy a presentar va a cargo del doctor Kalyan Moidev, aquí presente, y lleva el título de Evolutionary Computing for Efficient Solution of Practical Problems. Les voy a leer de manera resumida el currículum del doctor porque es muy amplio, verdaderamente muy amplio, y dice: Kalyan Moidev is a Cohen Endowed Chair Professor at Department of Electrical and Computer Engineering en Michigan State University. Él es de la India, pero está actualmente trabajando en la Universidad de Michigan. Sus intereses de investigación están en el campo de la optimización evolutiva, su aplicación en la optimización multicriterio, en el modelado y en el aprendizaje de máquina. Ha sido premiado con diferentes premios, entre los que destacan el Infosys Prize, TOAS Prize in Engineering Sciences, Kahastur Mandami Prize, Distinguished Alumni Award from IIT, Kharagpur, Edgeworth Pareto Award, Badnagar Prize in Engineering Sciences, and Best Research Award from Germany. Es miembro de la IEEE, de ADME y de 3 academias de ciencia e ingeniería en la India. Un detalle importante que muestra la capacidad de calidad del trabajo del Dr. Dev tiene más de 450 artículos de investigación con más de 125,000 citas. Entonces, una prueba de que no es solamente escribir, sino que hay que escribir bien. Y bueno, para ya no abrumarlos con más detalles, le cedo la palabra al doctor.
Thank you very much. Okay, the slides are up. Thank you for inviting me to this conference. Thank you to CDTech and everyone who are involved, Efren. I'm so glad that so many of you are here, despite the rain outside, but it's probably something you're very familiar with here sometimes. Yeah, so on my way here, the airline lost my baggage, so what you see me is complete Mexican. Everything here is brought here, just so that I can stand here and talk to you about. All right, so I'm going to talk today about evolutionary computing and then how this can be used to solve various practical problems, okay? And this is really my experience over many years of solving these problems. So most of the applications that I'll show you here are where I was involved, but there are many other activities and applications that people have done. They're in the literature. But I thought I have done enough to show you some example case studies. So you can see here, there are some people here like Oliver Sutze from Sina Vista, who's been doing a lot of work from there, and also the CDTech people and Efren and others. Carlos Coelho from there as well in Sina Vista. So you can look into these. If you search with these evolutionary computing, you'll find it'll take you to various different applications that people are doing. So these are very much into a real thing these days, because a few years ago people still thought, oh, these are still in the research stage and we are not even ready to apply them. But almost every day we are using them with real industries. Okay, so that's the idea I'm going to show you. So here, before I start, this is Michigan State logo, Spartan. And then this is the NSF center called Beacon Center. It's a study of evolution of action, is what I'm involved with. And this is my lab called COIN, Computational Optimization and Innovation Laboratory. In short, we call it COIN. So here's my email address and my personal website. From here, you can get to the lab website as well. Okay, so I'm actually a chair professor at the Department of Electrical and Computer Engineering at Michigan State. I also have a position in mechanical engineering and also computer science and engineering. I do that mostly to have students coming from those departments. Okay, so I would like to briefly talk to you about the scope of optimization in different practical problem solving, and then this particular evolutionary computation as an optimization process, which has actually borrowed the idea from nature, and then the niche of evolutionary computing in different problems. So one of the highlights of this is multi-criteria optimization, which I've been specializing for a long time. So later part of my talk is going to be on multi-criteria optimization. I'll briefly talk to you about these knowledge discovery aspects that I have been doing since about 2006. I find that that's an additional benefit we get for solving multi-criteria problems. I'd like to show you the one example of what I mean. Okay, so this is a very busy slide. I'm showing you here problems that come from different practice, like modeling. You're trying to model a blast furnace where there are some inputs and there is an output. And you don't completely understand what goes on inside that, although metallurgists today know a whole lot about it, but not exactly what goes on. So one of the ways to do is first, like, can I make a model of this complicated system? And they come from many engineering systems like that. The steel has been produced since 1905, so more than 100 years. And we are actually take our car over a bridge made out of steel. We live in apartments which are built with steel. So still we accept that that's a very strong material. But there is no proof that whatever you do here, what is the output that you are going to get, whether it's going to be the best output that you could have gotten. You get some output, right? So a modeling will help you get that kind of pinpoint that if you give certain inputs, what would be the output before you actually make it. So these are very important tasks. Now, if you don't have the science, exact science behind it, you can still do it if you believe in the process and you have lots of data, right? So then you can take that data and try to model the actual system which is giving you that data, right? So there are various ways of doing the modeling, and optimization is one way of getting there. Then scientific experiments, some experiments are very difficult to do, very time consuming, cost effective. So you have done already 20 experiments spending a few hundred, thousands of dollars or maybe a few $1,000, and then you want to do another 5 more new experiments. Instead of randomly choosing those experiments, you can learn from the 20 experiments you have done already and decide where to do your next 5 experiments so that you can get maximum information out. So this kind of work can also be done with an optimization method. Then of course this takes the lion's share of the application of optimization in practice, design and manufacturing. Whatever you design, whether it's a mechanical component, electrical, electronics, aerospace, whatever, there will be some parameters. As you see here, there are some angles, there are some dimensions, materials, thicknesses. All these becomes your design variables. And then you say, okay, I'm going to design this for minimum weight or maximum safety or any kind of objectives that you can decide. You can have more than one criteria as well. And then you have to do some analysis using, you've all passed through these bachelor's degree courses where that's where we try to teach you there is given the forward problem where if there's a collision that happens from the front, what kind of stresses that will develop. And we have a finite element course if you're a mechanical engineering student. We teach you all that, but what we don't amply teach you is how to come up with the optimal design, sometimes how to do the inverse, because now there's a lot of inverse programming that comes in through the optimization where I want to have certain performance of this car. So when there is a collision, I don't want certain stress to be more than certain value. Can you give me the design? So it's just the opposite thing of what the forward design steps that we teach at the university, because it's easy to teach. If I tell you exactly what we are doing to the problem here, like there is a load of so much coming here, given the design, you can tell me how much stress is going to develop. That's called the forward problem. If I assign this problem to each of you, you'll get very similar results at the end. It becomes very easy for a teacher to grade because you'll have the very similar answer. That's why you prefer to do it at the university setup where there are 50, 60 students in a class. But the inverse problem is different. Inverse problem is, I tell you what I want, what kind of stress I want at the end. Can you give me the design? So just opposite. Now, it so happens that because you're specifying only one or two things, which will come from more than two design parameters, there's usually more than one solution that will give you the same output. Now, if I teach this in a university setup with 50 students will come up with 50 different designs, and a lot of teachers don't have that much time. But that's really what the industries want. We are involved with one such project now from the industry. They want to do the inverse part of it, and it's getting very, very popular. One of the ways to do this is through optimization again. Okay? Then supply chain and placement, these are combinatorial optimization problem involving scheduling and all that, bus routing and all these. So these are also solved using optimization methods. Optimal control is sometimes taught as a separate course. So in many situations, we need to control a system. Even a car, if you're thinking of an autonomous vehicle, there'll be lots of controllers inside the car based on who is in front of you, what is the traction on your tire, are you going downhill, do you have to reach a particular place within certain time, so you have a time limit, what is the fuel conditions that you have now. So based on all this, some controller has to say how much fuel to put into your engine, right? So all these are difficult control stuff. You can come up with one solution, but which will work, which will take you to the destination, avoiding obstacles and everything. But then there could have been another controller or control system which would have taken you the same place with a slightly smaller fuel cost maybe, or slightly faster. So unless you do an optimization, you will not be able to get to that. You will have one solution that works, but it's not the best solution. So when you're using optimization in any of these places, it is taking you towards the best possible solution. Market prediction is another thing. It's kind of related to the modeling. Well, you take past data and try to model the market or the system that you have there. It could be very noisy. And then you try to project it in the future to say, now that I have a model, can I use it to project next 1 month or 1 year? In terms of investments, this could be a very lucrative thing. If your model is very good, you may be able to predict it well and then can make some money with that. And there are some industries, startups who are doing all this now through optimization. Data mining, I think Efren is going to talk next more about data mining. So that's a very important area these days. Lots of jobs and lots of problems that people are solving, not only in engineering, medicine and social sciences and everywhere. So these problems involve a lot of classification, clustering, pattern matching, feature selection, all these different things. And every one of them, there is a optimization path that is there for you to solve them. So if you know optimization, you can solve all these things. And finally, the intelligent system design has something to do with optimization, because optimization promises you to find a solution in the search space that is the best, right? So if you choose your objective function and constraints accordingly to define your optimization problem, you can build in some intelligence into your final solution, right? So that's the kind of connection. So if you look at this thing sitting there, you may be thinking, I'm doing something, or I've learned something where it kind of touches upon on some of these. Then you are ready to look at the optimization literature and see whether some people have already used optimization in that particular aspect. The last one I'm going to talk about, I give it a separate slide because this is getting to be a very emergent topics, and some of you have already yesterday talked to me about it. It's called bi-level or hierarchical optimization. Okay, it's about 10 years kind of old, but still there are a lot of things needs to be done there. Actually, there are two levels here. One is more in the upper level and has more power than the other that is in the lower level. In this case, I'm talking about decision makers or governments, policy makers. They come up with some kind of taxes, and then the farmers who works at the lower level take those taxes as given, and then they figure out what they should do, what kind of crop they should do, what kind of fertilizers they should use. So they are trying to maximize their revenue, and they're trying to protect the environment. And these people are trying to maximize their production, profit, minimum cost, and all these. So each one of them have their own optimization problems, but they're interlinked. At the upper level, they can simulate the whole process and find out what are optimal for the whole system. But there are some kind of uncertainties that these decision makers provide, and that's why you get uncertainties over there. So it's very practical, and lots of problems even in engineering, we try to divide them into different hierarchies simply because it's easy to manage, right? For good management purposes. I mean, even in university, you see there are some admin people, and then there are some people who are doing research, and there are people who are doing teaching, and we do that so that we can manage everything well, right? So we divide our tasks into a hierarchical level. So that's practical. We also need optimization algorithms that are working at each level and talking to each other so that we get a much better overall solution. So these are computationally more difficult to solve because of the nestedness, because one optimization is inside the other. But we are coming up with smart algorithms, fast algorithms, so that we can solve these things. So these are very recent advancements in optimization. Okay, so if you look at all these different problems that I've just alluded to you, and try to get a mathematical aspect of what kind of objective function constraints we are talking about, they will be most likely non-differentiable. Most problems we solve from practice are non-differentiable, discontinuous, but all of you have done some optimization in your high school by finding the minimum or maximum of a function, and you know that first thing you have to do is take the derivative and put it equal to 0, and you get some solutions, and then look at the second derivative to find whether it's a minima or maxima. Those kind of ideas do not work out when you have constraints and you are solving problems where the functions are not differentiable, right? So you need to think of other ways of doing them, more iterative ways of doing them. Then there are discreteness in the search space because variables have to be discrete. Mixed nature of the variables, large dimensions. The dimensions can be large based on variables, number of constraints, number of objectives. Each one of them pose very independent difficulties. And in many problems, there could be two things that are large. And then it gets compounded even further. Constraints are nonlinear, making them very difficult to satisfy. There could be multiple optima that happens, like I mentioned on the inverse problem. Today I'm going to talk a little bit more about multi-objectivity. So you have multiple objectives that are conflicting to each other. Uncertainties in the variables in designing, in saying that, okay, when the optimization tells you that this dimension here should be 50 mm, but you go and manufacture, you are never going to get 50 mm. It's going to be with some tolerances. So if deviating from 50 to even 49.9 mm, if that makes the objective function and constraints really changing in their nature, the constraint was feasible, now it is not, and you cannot accept that, then you are in big trouble, right? So then you have to take that into account, that how much uncertainties there can be when I'm declaring my solution is 50 mm. You have to take that into account within your algorithm, and then you can handle and come up with more robust solutions, or robust optimization. There are lots of problems you're facing now where evaluating one solution takes hours to days. We've solved some problems where one evaluation takes 2 days in some occasions few hours is pretty common, but 2 days is an extreme. But we had to handle. On top of that, when it takes 2 days to solve a problem, one solution, they also restrict you. They said, okay, you cannot do more than 50 evaluations total, or 100 evaluation at most. So on one hand, they are time consuming. The other hand, you don't have the luxury to use even 1,000 solutions evaluation. So in a search space of, let's say, 20 dimensions, 100 solution is nothing. So you have to be very judiciously using, like I mentioned initially about scientific experiments, if you already utilize 30 of them, and now the next 70, you got to be really careful how you ask them to evaluate, right? So there is this kind of studies are getting to be very, very challenging to do, but they are practice. On top of all these, every design must be considered from different disciplines. If it's a aircraft wing, you have to look at from his strength point of view, you have to look at from his aerodynamics point of view, like lift and all that. You have to look at from the vibration point of view. So not one person is an expert on all of this. You need some aerospace engineers, you need some mechanical engineers, some structural engineers to come and work together. And each one of these groups are bringing in certain objectives, certain constraints, some new variables. And then you have to have, so if you want to take the whole problem as a whole and try to solve it like one big problem, you get into this large dimension that I mentioned. But people rather, what they do is they try to come up with a methodology by which you go discipline to discipline. You first solve one discipline problems, keeping some flexibilities there, some lower bound, upper bound. Then you move to the next discipline and try to solve it, and come back again to the and do into a good, with some iterations you finally come up with this. So this is kind of an art at this point of how do you do this whole design, but this is where we are with some of these practicalities. So as you see that these problems can be very different as it comes from different fields, and also you need now a very flexible and adaptive method to solve these kinds of problems. I'm going to broad brush here the different kinds of algorithms in two classes, okay? One is the point-based optimization methods. I mean, so far we talked about problems. Now let's talk about the algorithms. Algorithms are divided into mainly two categories, point-based and population-based. In the point-based, you start with one point. So sometimes the solution X is called a point in optimization literature, because in the search space of that n-dimensional search space with variables, it's just a point in that search space. So here, for example, there's a point I'm showing you on the objective function. You can start from here and iteratively move. So you need a transition rule that will say, given the X, what is the next solution you want to look at? And this transition rule here, the T that you have, you can design. And then you are creating your own algorithm. Or you can look at what people have done in the past, then you are following their algorithm, right? You can, of course, modify according to your problem and all that. So that transition rule takes you from here to there. You get Y, compare Y with X. If it has a better objective value and constraints get satisfied in a better way, then you can accept it and say X will become now Y. And now you apply a transition rule to Y and you get to another point. So that's how you go. If Y is not good, you leave it and you create X to have another neighboring point. And you do this until your termination criteria is satisfied. You have to put some termination criteria to all this. So these kinds of algorithm point-based methods have not much memory requirement because you need to just store two solutions into your memory, X and Y. They are usually local. By that I mean if you start from here, you can get stuck to a local optima. But if only you start from somewhere here, you can get to the global optima. But to start with, you don't know, because you will not have two variables. You may have 100 variables, right? No parallel processing, not much parallel processing you could do because you're just dealing with 2 points. They're very easy to do theory because you have a grittiness here. You always want to improve. If this transition rule is differentiable, you could do a lot of theory. With that, not very easy to modify because I mentioned to you about adaptiveness of algorithms. Because this is already given to you how you go from X to Y, there is not much you could do to modify it, okay? Oh. Moved suddenly quite a bit. Okay. In the population-based approach, you have a population to start with, and then one population create another population. There could be some overlapping between P and Q, and then you evaluate the whole Q with respect to whole P, and then decide what of P and what of Q will stay as the next iteration points Px. So we take both of them into account, and then we decide what's going to stay. So it could be some of the old population members and some of the new population members can become the new population for the next iteration. You keep doing this, so you also need to design here a termination rule. This could be several rules and all that here, and then do this until you terminate. So some of the properties of this is it requires memory, because now you have two population, not just 1 point, but maybe 50 points, maybe 100 points to store in your memory. Usually they have a more global perspective because you're dealing with number of points, so you can send your points at various places in the search space. So you have a better chance of getting to the global optima. You could do a lot of parallel processing simply because you're dealing with number of points. There's something called implicit parallelism that these algorithms has. One point helps the other point within the population because you are doing a lot of computations within the population. And they are usually more flexible to be modified because some of these methods we're going to talk about makes it very flexible. Okay, we need to know this theorem before we try to talk about what each of these methods are and everything. In 1997, Wolpert and McCarty came up with this no free lunch theorem. What it says is if you have two algorithms, A1 and A2, and you are trying to decide which one is better, A1 could be something you developed in your PhD thesis, the whole spending 3-4 years. So you really like this method. A2 could be something you picked from the literature. Okay? And now you take all possible problems to solve, and then you apply A1 to each member of this big class of problems, and you define some kind of a performance measure of how A1 did on each of these problems, agglomerate the performance, maybe averaging or whatever, and you get one metric that says P1. So P1 is a performance measure that's for A1 applied to each problem of F with a certain computer, with certain amount of time which you have fixed. Do the same thing now with A2, with the same computer, same number of evaluation and everything. You get an agglomerate performance measure called P2. They have proven that P1 is equal to P2. So that actually says that whatever you develop through your PhD thesis spending a lot of time is as good or as bad as any other algorithm if you are interested in solving all possible problems. So that's very discouraging for someone to work in optimization, right? And this is proven, okay. But it's not that discouraging because it breaks down if you are interested in solving a class of problems, okay? So that's really the background of my talking about customization. So given a problem class, like you're solving a gearbox, so one of those from the first slides I showed you, right? It's the car cab body. So you're only interested in doing that for that automobile industry. You can come up with one algorithm that will be best for that particular class. But if you take that algorithm you developed, apply it to an aerospace design, it's probably not going to be as good. So they kind of average out, but for a specific class of problems, you can work and research and come up with the best possible algorithm, okay? So it just says that there is a bit of research that is needed for you to come up with the best algorithm for a problem class, and it's worth spending that time because in industry, if you're joining a particular department, this is what you do. You don't do today these things, tomorrow another problem. You just have a small class of problems you keep doing rest of your life. So at some point you want to stop and say, I want to develop the most efficient algorithm for my class of problems. The industry people are understanding this philosophy and they are now willing to do that particular task. So optimization researchers with this theorem is going to stay. So it's a good news for optimization researchers that this is true. Otherwise, if you are sitting there and thinking, I'm going to be an entrepreneur, I'm going to come up with one code of optimization and sell it to solve all problems, and in my box of that product, I'm going to say, this software can solve all your problems, you'll be in trouble because somebody knowing this theorem will say, you're violating NFL, right? Because you can't do that. Okay, so getting to the evolutionary optimization, which is a population-based approach. Motivation came from a lot of natural designs that we see around us. With nature, with many years of experience and trial and error, have come up with very efficient designs like these stiffeners that reduces the buckling. A lot of nonlinear equations needs to be solved before you can find out how frequently you should, what is the length of that gap that you have for these stiffeners and how stiff they have to be. This is basically 3-4 days of lecture we do in an applied mechanics class with lots of PDEs that you have to solve. So you wonder how nature has done that. Nature cannot solve PDEs, right? Similarly, all these objects that you see, this hexagonal shape is really the optimal shape for minimum mass. I think it's the maximum stiffness per unit mass. How does B know calculus and come up with this hexagonal shape? So it's many years of trial and error. If we can take the concept of how they are coming up with all this and try to speed it up on a computer, maybe we don't have to wait millions of years before we design something useful, but we can speed up and get it. So that's the whole concept. So with that, whole evolutionary optimization idea came in. So basically mimicking nature, taking the principles from there and trying to solve something from nothing to getting towards a very good design, right? So that's the concept. What I will argue at the end is if you just keep it this way, like a vanilla algorithm, like you start there's a button you press on your computer, you have the algorithm already set in and come back after 3-4 hours and you expect a nice design coming up, it's too fancy. It's too much to expect. You need to customize, as I said, okay? And that makes it more feasible, more viable to do. So here is a sketch of an algorithm. You start with initializing a set of points, evaluate to find which are good, which are bad, And then while not terminating, you select the good ones using the Darwin survival of the fittest kind of concept and call this a mating pool. And then you use the mating pool, which are good solutions of the PT, and apply a few operators there to create a new population. We call it an offspring population. Evaluate the offspring population. These open circles could be those offspring population. So you've evaluated them. Now you combine the whole PT and QT together and apply a survivor operator to decide which is going to survive for the next iteration. And then you increment the counter and go into the loop. So it's a very simple algorithm. There was a competition a few years ago in our Gecko conference. The competition was who can write, using any programming language, the shortest possible code implementing this concept. Okay, so it's an open competition. You can use any programming language. Guess who won? What language won? It was MATLAB with 18 lines of code. Somebody came up with this, and there were some test problems which was put out there, and it was solving all those problems. Okay, so this could be a very simple idea, but then each of these red words that I put here, including the termination, this should have been red, you have the place where you can go and change them, use problem information to make it more customized for the problem that you're solving, starting with initialization to each of these operators, right? So it's a bit of onus on us. There's a bit of learning curve of how can I change these things so that I still have a good algorithm. For that, you need to study a little bit, maybe take a course on this. But once you do a few of these, you get a hang of it, you know what is the good thing to do, and you can customize your algorithm for different problems. I'm going to skip this one. This one actually was showing that how, for a very simple design of a diameter and a height as two variable in a CAN design, you do start with initial population. Some of them can be infeasible, so you can assign some artificial cost to tell them that they're not good designs. You use a selection operation, which we usually do is tournament selection, play tournament among them and decide who is going to survive. You see that in that process, the good ones here, the minimum is better. The good ones have got 2 copies, like 23 has got 2 copies, 24 got 2 copies, but at the expense of these 2. These 2 are bad, got deleted. So this is the Darwin survival of the fittest idea that weeds out the bad ones and make more copies to the good ones. And then you can apply some operators like recombination and mutation, where you take these solutions. It depends on how you're coding these variables. You could do it binary coding, you could do real, and then do some kind of exchange. So here I'm doing a very simple 1-point crossover where between the 2 parents here, the left part of this cross site chosen randomly is swapped, is kind of combined with the right side of the second parent. So this with that, I get a new one, and this with that, I get another new child. So these are called children, and these are the parents. And some of them may turn out to be good, some of them may turn out to be not so good. But you just do that anyway. It's a mechanism by which you create these solutions. Sometimes you do mutations where some of the bits can change to its complement, and then you may get a better result, you may not get a better result. But if these are good solutions and you are using some problem information now here to decide which one of these bits I want to change, maybe you can increase the chance of improving the solution more, and that's what I mean by customizable, right, or customized algorithm. So putting all this together, you can see how they work on a very simple 2-variable problem. Here, the 2 constraints are kind of inactive at this point, starting with the same initial population that quickly, very quickly decides that this is the initial point we should be crowding around. So all these points come there, and then you can see from here on, you can leave GA and use a point-based method. So a hybrid method would be very good. Here is another problem where they've changed the sign of the constraints. Now this part becomes feasible. Optima changes from there because optima cannot be infeasible. And you can see starting from the same initial population, how this algorithm decides that they have to come that way. They have to have more preferred points here and come that way. So without changing any parameter. But these are only 2-variable problems. I will show you later a very large-scale problem. These ideas are used in real world. I'm showing you here 2 or 3 examples. This is the Japan Shinkansen, the bullet train. They designed it in 2006, started operation from 2007. I believe they're still in operation. So if you have a chance to go to Japan and take a bullet train, just go in the front of the train and appreciate it and know that the nose of these were designed using a genetic algorithm. Why? Because they tried to use a point-based method. It failed. It got trapped into a local optima. When they then simulate the process on a wind tunnel, it was not passing the constraint tests that they had. So then somebody told them they should use a more global approach. GA was one, and they used GA, and that passed the test. So it was a big news when it came out And I happened to be there in that meeting, so it was very nice for me to see how the whole thing have motivated them from going from point-based to the population-based and getting with something. So now they have an algorithm they use every now and then. They're still modifying it. You can see lots of features in it, right? All these are design variables. So that's what they're trying to arrive at through this optimization. This is Kone's lifts. So in a high-rise building, you have lots of such cars, and you go at various floors and press a button that you want to go down or up. All this information are taken every half a second. And an optimization using GA is run immediately. And a solution is found immediately, and then the cars are allocated to go to this. Every half a second, this is repeated. You wonder, what kind of processors do they have? What they have done to make it every half a second is they have taken the software that they developed with GA, converted it into a hardware chip. So everything is happening at the speed of light. Okay, so it's very, very fast. An optimization is coded in hardware to get the design. And just to show you that they are actually using GA for allocating landing calls. This is taken from their manual of how they're doing. They've been doing it since '95, so for a long time. All right, so with all these different things, these algorithms have their own niche. So algorithmic flexibility is, of course, one thing where these algorithms are being liked. You can change in any of these places I mentioned. Some people are taking advantage of the population approach that they have. I have taken it, and many people who are working on multi-criteria have taken it, because in a multi-criteria problem, naturally you have to find multiple solutions. So you have a population here with this method, so you can store those multiple solutions in the population, right? So that's one big advantage for us to go and use this for multi-criteria optimization, and we have really exploited that. It's a direct approach. There is no need for gradients. But if you have gradients, don't ignore it. We've solved some problems from industry where they have already supplied us some gradients. So it's coming free to us. So we changed our algorithm, like mutation operator with a gradient-based technique, and that helped. So if gradients are available, gradients is not our enemy, okay? They are available, we should embrace it. But what I'm saying here, it's not needed. And if you're not using the gradients, that means they're not available. Your algorithm may be a little slow, because gradients can give you a shortcut. But you also have to know that gradients can take you to the local optima. So you got to be careful with how much you use that. But usually they're direct approaches. And they can solve procedural definitions of objective function and constraint. Like I cannot define the objective function mathematically as a function, but I can write a little code. And at the end, I can get my objective function and constraints. These methods are great for those things, okay? All right, let me skip some of these. This is in the robotics that we've done a few years ago. But getting to the customization concept, this should have been a capital A, evolutionary algorithm. It's a big question now. How do I customize? Okay, I see that you have solved 3, 4, 5 problems. But to my problem, what do? I get this question all the time. So we need to formalize some of these. We are getting there, but there is not even a single paper to formalize what is customization. How do you do customization? I can show you some examples, and you probably get the idea, and then if it kind of falls in your problems, you can use it. So here is one. If I have a problem where I know my x1 is bigger than equal to x2, x2 is bigger than equal to x3, and so on and so forth for all the variables, there is this pairwise relationship. Where is such a problem? You can see this problem, for example. It's a cantilever beam. Those of you who are mechanical or civil engineering know this. You apply a load here. You expect that this one is going to be much more thicker than this if you divide them into small components and make it that way. So you know that x1 is going to be bigger than equal to x2, x2 is going to be bigger than equal to x3. They can be equal, but this one suddenly is not going to be bigger than x1, right? That defies our engineering education, and that we all went through in our undergrad, right? So that's the engineering knowledge and expert knowledge that I have from my profession. I want to somehow utilize it in my optimization algorithm. Ignoring it will be foolish, because then I'm kind of saying I didn't have any engineering degree, okay? And I don't know anything about the problem. But no, and this is about engineering. But think about someone in a company working like 20 years for that job, and now you are going as a fresh graduate and saying, oh, I don't need your expertise. My algorithm can find everything what you know. It's really demeaning, right? And it's also, it may, if your algorithm is smart, but why do that if you can ready-made get that information? So that's what I'm talking about. once you get this knowledge that this is what we have in our problem, so let's see how we can utilize this. You probably will not be able to utilize this in a point-based methods because you are following a steepest descent. It always says go along the negative of the gradient, and it may not happen that every point you have the gradient, these kinds of conditions are automatically satisfied, right? But what you could do is take these variables in a GA and change to a different set of variables. X1 is still the same, is the first dimension. Instead of doing X2, the next dimension, you redefine a variable called P2, where P2 is equal to X2 divided by X1. And you restrict the upper bound of P2 to be 1. So if P2 goes between 0 and 1 means X2 can be always less than or equal to X1. So now you can use a random number here between 0 and 1, random number here between 0 and 1 and all that. You are making sure that this is always satisfied. So something you wanted to honor, I have got a coding by which I can honor it at every solution that I create. You can't beat such an algorithm because if you randomly create X1, X2, X3, most of the time you are not going to be satisfying so many constraints. So this is a simple idea which you can just change something and make it happen. Another one I'm showing you here is if you're particularly dealing with that market share thing I told you, you want to invest all your money into N stocks. Okay, and these are proportion of your money you want to spend in stock 1, X2 is proportion of your money you want to send in X2, stocks 2, and so on and so forth. Obviously, when you sum, all your investments should be 1 because you want to spend 100% of your money. So this is a natural constraint, comes in certain problems. Now you know that all the X1s have to be a fraction, 0 and 1, 0 and 1. So create a random one here to start your algorithm. I can guarantee most of the cases the sum is not going to be 1, right? But you could do this simple trick. You create them randomly between 0, 1, 0, 1, 0, 1. Now divide each one of them by the sum of them. And then you have a new variable for each of them. Now when you sum these new variables, it will be exactly equal to 1. So you're always satisfying it by doing this simple repair of your vector before you compute the functions and constraints. Okay, some of these things are difficult to do with point-based methods. There are many other things that we have worked on, many problems we try to look at these kinds of simple thing. I want to show you this example because it's an extreme scale optimization which we had to do for an industry problem. So it comes from a foundry, you melt some amount of metal and then you have to pour it to make some castings. Okay? So this particular company, PTC Industries, they had a vessel of 650 kilo. So 650 kilogram of steel you melted. Now you are going to make some molds. There are lots of options in front of you. So you make few of them, say you have utilized 630 kilos. 20 kilos are still there, but none of them is less than 20 kilo. So that's a waste because you can't have done a casting and come back after 3 hours and pour the rest, right? You can't do that. You have to either completely do it or not do it. So then you thought, if I use some other combination, maybe I could have utilized 640 kilos. So you would have a lot of material utilized. So we tried to, this company came to me and said, we want to maximize the metal utilization every time we melt. I need an algorithm now because they're not doing it one time. They're doing it many, many times, in fact, for the whole month. I quickly calculated by formulating the problem, how many variables are we talking about? It comes to around 50,000. It's a very large number for any optimization standard problems to handle such a large scale problem. So we know that maximum metal utilization could be 100%, but depends on the sizes and the vessel size. You may not always get 100%, but it will be something very close to 100% is where is the optimum, right? But we don't know beforehand for a problem. So here is an example. I formulated the problem. X is my variable. You see that in the objective function, the constraints, X is coming linear, in a linear fashion. So it's called a linear programming, except that all the X size has to be an integer. Like I said, I cannot do 1.5. One full and another one of the same one, I make 50%. No, I cannot do that. Either I do 2 copies or 1 copy or 0 copy or 3 copies, something like that. So here is a solution with 10 orders and 10 hits. The first hit of 650 kilo says, make 1 copy of second one, 1 copy of third one, 2 of 7, 1 of 8, and you'll utilize 623 kilos, and you get a utilization efficiency of 95.85. Second one, you do this way. Third one, you do this way. When you take an average, you have 95.05% efficiency as your overall objective function. This is the one you want to bump up to get as high as possible. So that's the optimization problem. And these variables for their industry problem will go to 50,000. Okay, so that's what we're talking about here. If you look at the classical algorithm like point-based methods, we always try to do that because we came late. They have been doing for many years, so you always have to justify why you are using a GA or an evolutionary method. So we tried this branch and bound method, which is the way to solve this problem. There are several variations of that. But there are good softwares that are available. IBM Simplex is one very commonly used. You go to any OR conference, they will have a stall. They show you all the things that they do. But they have a component called branch and cut method. It's a fix-up. It doesn't scale up. But linear programming problem with real variables as x, you can solve hundreds of thousands of variables without much problem. But if you have integer variable, they are very naughty. So it's very difficult to solve. It's an exponential idea. So I took a very simple example requiring only 31 hits, requiring 20,000 kilos of metal. So the vessel size that I have requires 31 hits only. So I know that's the optimum, but I can solve the problem with 32 hits, 33 hits, anything more than 31 very easily because I have more material to fill all these. So there will be a lot of waste, but that will not be optimum. And I'll show you with the Simplex, I can solve that in 0.05 second, piece of cake for Simplex. With 99.256%. This is the optimal solution. Then I move to 1,000 variable. It takes a little more time, but nothing much really. And I get the optimum. I go to 2,000, it cannot solve it. That's exactly what happens with point-based exponential algorithm. There will be a point, a number of variables beyond which there is a curse of dimensionality in optimization that's called. There is a curse that dimension gives you to your algorithm, says anything more than that, there are too many variables to handle, and it cannot work it. So we try to see between 1,000 to 2,000, where does it stop working? And we found that 1,800 was that number for this case. So I looked at the 2,000 variable problem, and I've printed out some things at every iteration that it's doing. The blue ones here shows how many nodes, this node that I'm talking about here. Okay, these are called nodes, and when I put a line means this is already stopped, so I don't have to go any further. So you get an optimal solution when all the open nodes are fathomed or bounded. So that's the idea. So by 30 minutes of my run on my computer, there were about 35 million nodes that are open for a 2,000 variable problem. Remember, I have to go to 50,000. So by 30 minutes, it will be really much more. Okay, so it's opened. And then this side, the red line shows how many of them are yet to be closed of the 35 million. Still about 35,000 are yet to be closed. So I thought maybe another few minutes and we'll solve it. So I ran it all the way up to 15 hours. Both of them are still growing like this. Okay, so that actually says the dimension is too big for this algorithm to stop everything, to bound everything, and give you a solution. So what do you do in this case? When it's a standard software, and you have to solve the industry problem, you need to start thinking of customization. Okay? How do I make an algorithm which is flexible enough for me to change and make it to work for these kinds of problems? So we came up with a custom-made algorithm for this particular problem. So we have a custom initialization. One of the constraints, remember, was this, that some of few variables here, let me see, some of the variables should be R. I showed you one where x1 plus x2 plus x3 is equal to 1. I have a very quick way to satisfy it. Those kinds of ideas are used here. So I do a very nice custom initialization, and then I do a custom recombination where I take two parents. I'm showing you here with just 4 hits and 10 different orders. And these are two solutions. I go hit by hit and compare this one, the first hit of the first parent with first hit of the second parent. And I notice that first parent has utilized only 343 kilo. Second one has utilized 625 kilo. So which is better? I have a vessel size of 650. Obviously, this is better, right? Because it comes close to my limit. So I take that and put it in my child. Then I look at the second and second, 808, 667. None of them is valid because I melted 650 kilo. But this one says you should use 808. This one says you should use 667. None of them I can use. So I need to fix the problem. But just at this point, which one is better? This one is closer to 650, so I take a copy, put it here. Go to the third and third, 629 versus 606. This is better. I take a copy, put it here. So this is how you keep building your child. Okay? When you do that, it's a perfect crossover. We are taking good aspects from two different parents, putting into one child. But in that process, we are screwing up the constraints. Now, I treat my mutation operator to fix these constraints rather than just a random perturbation. So again, a custom mutation, which I'm not going to go into details, but it's sort of like a game. I have to make here, it's now 3. I need to make it 2 because that's my demand. So I need to basically take one of the ones and make it to 0. Which one? I can look at these things and do. So there is an algorithm I have which has this kind of complexity. This mutation operation, which I call repair operator, is guaranteed to satisfy all these demand constraints, the equality constraints. Then I have a mutation 2 operator, which I call repair 2 operator, which tries to fix these things. Some cases we can, like you see here, but some cases we cannot with one iteration. Then we just leave it there because we don't want to spend too much time doing the crossover and mutation. Okay, so look at these results on 310. Simplex took 0.05, we took 0.04, same accuracy. 1000, same accuracy, slightly smaller time, but the good thing we're able to solve it. 2000 variable, Simplex could not. Now we get the optimum with 0.19 seconds. So that's 2000 variable, but we have to go to 50,000. Obviously, our algorithm worked and we gave them the code. Then they said, it's a nice thing. We are not supposed to publish it. Okay, so they want to keep it for them for some time. I said forever. They said no, after 3-4 years is fine. So I had to wait 3-4 years before I could do further study. Okay, we did the study, but we did not publish it anywhere. Now we have the results for a very large scale problem, which the company is not interested, but for academic interest we show this. So there are a couple of things I want to show you before I take you to the multi-criteria, is that this is a very typical performances that you get with population size. These industry people don't know what is a population. They don't have anything. They want to solve the problem. This is our algorithm requires a size, initial population, and then there's a population we are carrying. So what is the size? So you do this parametric study starting with 6, 8, 10, and all that. We notice that the performance improves as you increase the population size with our algorithm. There exists a point where it just starts to work, but sometimes it works, sometimes it doesn't when I start with different initial point. But if I go somewhere inside here, every time it works, because there are 2 bounds here. You can't see it here because they work really every time the same way. But you don't want to go too far from this range because it is unnecessarily taking a lot of solution evaluations. So here is the sweet spot, okay, between 30 and 50 here. So we suggested them to use 40. So they don't have to worry about what is population size. We hard-coding says use 40 as the population size. So you need to do some of these. Was recombination needed, or just the mutation of repairing was good? And here we show, no, if you don't do recombination, it doesn't work. When you use 2 parents in your recombination, that really starts to work nicely. Anything more works, but it takes more evaluation. So we fixed it to 2. So these are some parameters we have in our algorithm, and you need to do that study with your algorithm. Make sure it works in most of these problems. All these testing was done on a 1 million version of the problem. Okay, so it's a very large problem that we tried it on. Here's the big picture. From 50,000, which the company is interested, now we are able to give them a solution in 10 seconds, less than 10 seconds, as you can see, to all the way to 1 billion variable. Okay, not many people have solved such a large-scale problem yet. There are just few studies with such a large-scale problem because it doesn't come. And this one, the company is not interested. So we are doing this to show that our algorithm can scale if you think properly. So that's the whole idea. This is in log scale. This is in log scale. If you got a straight line, means it's a polynomial performance. With the slope tells you the order, it's less. It's more than 1, less than quadratic. So it's a very high, very good polynomial time algorithm. If you look at the problem formulation I gave you, it's an NP-hard problem. So you should not get a polynomial time performance. But all these points are not optimum. They are, I put a setting that as soon as I get 99.7% utilization, I will stop. Optimalize somewhere from 99.7 to 100%. But in this study, we said for practical purposes, we won't, because we knew this is an abstract problem and we don't have a polynomial time method. So if you want to go from each of these points to the actual optimum, which is between 99.7 to 100%, you have to spend an exponential time. And if I plot such a thing here, the exponential, it will probably go like this. So by the time you are billion, it will probably take a million years for you to solve that. So that's the nature of these exponential algorithms. So the question now is, is this any good to you? Or these are all junk because you're saying none of them is an optimum, so I'm not interested in it. That's the good practical question. To most industry people, this is good enough. In fact, the industry says, give me a 90% utilization, I'm happy, because they are trying hard to get, their current results were 70 to 75%. So I'm giving them 99.7. Why this odd number? Because that's about 2 kilo off from 650 kilo. So I back calculated and says 2 kilo is probably okay to tolerate. So that's usually happens in practical problem, that if you are willing to accept an approximate solution, then you can get a fast algorithm. But if that's not what you want to do, you want to really get the optimum, then you have to wait like lots of time. Okay? So that's the message I want to give you. The problem is still exponential, that's shown by here, that as you get more and more accuracy, the time needed to solve these super exponentially increases. Okay, so with this kind of single objective and evolutionary algorithm and what it's good at, as you see that as the problem gets more and more complex, either through variables or more complex nature of the problem, like the bullet trend that I talked to you about, evolutionary methods get an edge. So that's really it. And they are not exact optimizers. They are very good approximators to the optimum. So if that's okay for you, you should look into this. Okay, I probably don't have much time, right? Okay, let me take 5-10 minutes just to talk a little bit about multi-criteria optimization. So here, now you're talking about not just metal utilization as one criteria, but there are more than one. So you may have a cost you want to minimize, and there is a solution that's best for that, but you have another criteria that you are also interested. For that, this solution is not so good. So if you want to optimize this, you get another design for which this criteria is really bad. So that's the kind of trade-off you get. But you might think these are the two solutions of these two criteria problem, but it so happens there exists a Pareto set where there are lots of designs here, comes on that red line, that each of them is a good candidate for this two objective problem. Okay, so now the question is, how do I find this set? And it so happens by theory that this will always be, if you're looking at the global Pareto front, it always be the edge of these objective space, which I'm showing you here in blue color. Okay, it's not going to be in between. Okay, it's a feasible objective space. So first question is, how do I get there? Second question is, how do I distribute my points so that I'm giving a good idea to the user of what is the nature of the variation? The third question is, which one shall I choose out of this? Because here I've shown you 1, 2, 3, 4, 5 cars. But which one shall I buy? Sometimes the decision maker says, don't give me 10 design, give me one. But which one shall I do? Because I don't know his preferences, right? So you need to have some preference information before you can choose one. So there is an optimization concept, and there is a decision-making concept. That's why these kinds of multi-criteria problem has multi-objective optimization and multi-criteria decision-making as two main ingredients, which I'm showing you here. There are classical ways of doing it. Weighted sum can give you a point with combining the objectives with weights, and you get one objective function. You can get a point which is Pareto optimal, but you cannot solve problems like this where they have non-convexity, and none of these points over here from B to C can be found by this method. So it's a nice idea that you can, very intuitive idea you could do, but know that it doesn't work all the time. There are other methods to fix it, but very early on in early 90s, we came up with some algorithms with this principle that we are going to separate the optimization from decision making. First, we are going to treat it like an optimization problem, get a set of points which are nicely distributed and well converged, and then we will go with these solutions to the decision maker and let them pick one from it. So there are two separated problems. More and more what we are finding is this diagonal step, which is our interactive step, where as we are optimizing towards the Pareto front, we also collect preference information from decision maker and kind of narrow our search towards the preferred point or region of the Pareto set. So these are some future things that are yet to come, but there are some research that's already been there. So that's the interactive emo that I'm talking about. There are lots of algorithms. This is a very celebrated one. It was published in 2002. I think right now we have over 32,000 Google Scholar citations for this one work. Quite a few software industries have adopted it. They have a button called NSGA2. For 2 and 3 objectives, it works very nicely. by combining the parent and the offspring, doing non-dominated sorting, and maintaining diverse solutions through crowding distance. Because of time, I'm not going into the details, but you can find it in the paper. But this is how it works, this side. For 2 and 3 objectives, for 2 objectives, if these are the 2 objectives you're trying to minimize, here you get a parity front. And starting from this set of points, you saw how they came down to that. Here is our new idea called NSGA3, because this algorithm do not extend more than 3 objectives. We had to work hard to get to this algorithm in 2014, where you can see in 3 objectives, F1, F2, F3, how you get a set of points describing you the Pareto surface. Okay? This case, it's a very well-defined problem, so you can see nice structure. But in a practical problem, this surface is not so smooth. And these kinds of algorithms can get it. So that's about optimization. There's a whole lot of literature there. We're still working on how to combine point-based with evolutionary so that we can have fast convergence with good diversity. But then let me talk a little bit about the other part, the MCDM part, the decision-making part. How can I choose one? Okay, so if you have some information, let's say you're doing F1 and F2 in a deep neural net architecture search, for example, you might say, I want to minimize my error of predicting of what's going to happen or classifying an object. I want to minimize the error. I also want to have an architecture that is simple, that is not very complex. Not many, the tree size is small. So if you do that, you can get a Pareto front. This is a hypothetical one. I'll show you one that we've got recently. But now, before you even solve it, you say, I have a reference point. I have an aspiration point. What does that mean? I'm looking for some kind of complexity estimate, which is here 0.1, and some kind of error estimate, which is 0.8. Let's say I've set that as a threshold. If you can give me one solution that satisfies both these over here, I'm happy. Basically, what you're saying is give me a part of the Pareto front that is close to this point. Okay? So I'm not interested in these points anymore. I'm interested in that one. So this is some way you are telling the optimization researcher beforehand what kind of region you like in the Pareto front. If you can describe it 1, 2, 3, or many points, we can go and find these respective part of the Pareto front. So this is called RNSJ2, which we suggested way back in 2006. There are some a posteriori approaches, like starting with optimization, ending up with the decision making. This is a compromise programming approach you can apply when you get this set of points, find the ideal point, and simply go and find the closest point to the ideal point. That's one of the ways a lot of chemical engineers do their process planning problems. There are marginal rate of substitution ideas which you could do. From every point, go in the left and right in the neighborhood, find out the trade-off. That means going from here to there, how much you gain and how much you sacrifice on either side. And then you define a metric which could be sacrifice per gain. And then you look for the one that has a maximum sacrifice by gain, which means that with a similar gain, you need to sacrifice a whole lot if you want to move to its neighbor. So I have no motivation to move. So that's a very much nicer way of choosing a point than the previous one. There are other methods that exist as well. Okay, couple of slides on deep neural architecture search, because I know there are many of you who are doing this. It's really recent hot topics in machine learning area. We developed NSGA net. So it's a 2-objective neural architecture search algorithm that we have. You can see the performance of our algorithm. Okay, these are the vanilla NSGA2. So we have a customized NSGA2 for this problem. And these are the results here. And these are the points and how we have come there. But it's basically you have lots of different classes of images. You take the images as a colored pixel. And then there are like 1,000 images per class, and there are maybe about 1,000 such images. And then you separate out some test images and see how well your algorithm is able to work. These are some of the networks we came up with, A1, A2, A3, A4, as you see over there. But let me show you the comparison. So here, on some classes of problem, this is Cypher 10, Cypher 100. We also did for the ImageNet datasets, which are much bigger. With some standard algorithms that people have done, including the Google DeepMind, look at the advantage we get. We get better accuracy, so 95.33 is better than 94, and we need 0.2 million parameters in my network, so it's a relatively small network, compared to this one, which requires 1.7 million. So we have about 18.2 times advantage, and better accuracy. Same thing with other algorithms. And if you look at how our NSGNet performed with respect to other methods, you're trying to maximize accuracy, minimize the number of parameters. So our frontier is dominating the other algorithm software, including the DeepMind algorithms, which are using very large number of GPUs. So they are mostly relying on the hardware, the fact that they have money to get lots of GPUs. And in university setup, we cannot really have so many GPUs. We are dealing with 18 GPUs only. And we are basically relying on the algorithmic aspect of it. They are relying more on their hardware aspect of it. And we are showing with the proper software design, you can beat the results of a hardware design, okay? So these are nice, and this paper got the best Gecko paper award this last summer. Okay, one or two things about the knowledge that I mentioned. It's a very important thing these days. Once you get the Pareto set, you will have different looking solutions. You can study them because they're all optimal. So if you study them to find out common features, they stay as a knowledge. They stay as very vital rules for solving this particular problem to optimality. We've done lots of problems. Here is a gearbox design problem having 28 variables, 101 nonlinear constants. It's a real gearbox design problem. What we found is that the module has a nice relationship with one of the objectives. So if you want more and more power delivered by the gearbox, your module has to be higher. That is how you increase your gearbox, because doubling the module, double the sizes of the gears. And this is the recipe of solving that problem. All other variables you kept more or less the same. So 27 of the variables you have to keep same to certain value. Only module you have to change in a way. And when we fit a curve through this, it turns out module varies proportional to the square root of power. So you get a lot of thumb rules derived out of the multi-objective results. They stay with the designers as a deep knowledge to solve the problem. Okay, just to finish my talk, there are a lot of practicalities we have now embedded in our NSGA2, NSGA3 algorithms for handling uncertainties to get robust solutions instead of just optimal solutions. Then we get to reliability-based design, because now when you have constraints, you need to provide some kind of reliability against failure. So we could do all that now with the chance programming idea. So again, I'm skipping some of these. We've also got bi-level optimization, the one I mentioned, with multi-objective at every level. And that introduces really a completely new area of research. We are always using surrogate-assisted ES here because that's the way you speed up. You call the lower level minimally. Okay, we tried this on real agroeconomic problems. This is Iowa raccoon watershed, where the farmers are living here, and they are utilizing all the tax policies that I mentioned to you, what kind of fertilizers, what kind of crop they would grow. And the objective is all these fertilizers, nitrogen and phosphorus, is washing through these rivers and finally getting out of this as a loading, as they call it, and those are bad. Okay, so you need to minimize the bad things that's been thrown out of this, and then maximize their productivity and all that stuff. They are in conflict. So we have actually nicely solved some of these problems with 2 criteria and with uncertainties. Okay, so there are many, many other problems we are solving in various disciplines. But to summarize, I basically wanted to highlight the need of optimization in practice, and hopefully you've seen that today. Sometimes in the literature, the optimization is mostly portrayed as a way to find a one solution, right? But if you use multiple criteria, you can get multiple solutions, which are equally, which has a trade-off. Knowledge of that is useful, and then you can learn a lot of rules of how to solve the problem. The classical methods provide foundation. The point-based methods, you cannot ignore them. So if you want to be working in this field, you should take a course on classical optimization methods to know what are these methods. Sometimes we use those methods within our algorithm. Evolutionary methods enable to find a near optimal solution. And if you really want the optimum, then it's better that you club this with point-based methods. That's the best way to do. Customization, I hope I try to convince you that that's really the key to solve large-scale complex problems. It's not a magic anywhere. Multi-objective optimization comes with a bigger cause and more practical, more viable way of solving problems. I think the whole thing together is very exciting to me, because it just touches up onto so many different problems that if you know some of these methods, you will have a job. So that's my last word. Thank you very much for paying attention. I'm not sure if there is any time for questions, but if there are 1 or 2 questions I can take.
Vamos a pasar a la sesión de preguntas. Si alguien tiene alguna pregunta, por favor.
Oliver.
Yeah, thank you for this great presentation. I have a technical question on the steel problem.
Yes.
The results are absolutely amazing.
Yeah.
My question is, did you also try to modify Simplex? Maybe did you try to run it on the P space which you have done?
That's a good things. We can modify Simplex. We can modify our methods also. As I'm presenting these at various places, I got another idea. We can structure the problem and do much better job. But yeah, I guess we can improve. Maybe if we put a bound on the Simplex also with 99.7%, because all you are expecting from the Simplex is the real optimum. But if you have a constraint that says, I want the 99, maybe I can solve this thing. So we need to go back and do these things. But what I was trying to show you is how these standard methods takes unnecessary more time if you're really interested in the optimum. And if that's the case, you can design some customized algorithm that can be competitors to them or even better to them. So my goal was not to just solve that problem and show you this particular problem I can do. The idea was that you can have to design a customized algorithm. If I used a standard GA downloaded from some website, I wouldn't have gotten such results. But if that's the problem I have a competition on now, that who can come up with the best algorithm, we can maybe come back with Simplex with a much nicer idea, or a combination of Simplex with Evolutionary, maybe a better way. That's a different question, but it's a very good point. Yeah.
Thank you.
Thank you.
¿Alguien más?
Over there.
Hello?
Yeah.
If you don't know the function or whatever, if you don't know the function you're dealing with, do you try to spread as much population throughout the space to get the global, near the global?
Yeah.
Or do you tend to put most of the population on the maximum or minimum values?
Good question. So he's saying that if I don't know the function, but I have the search space, where do I start my points from? So there's an initial population I mentioned. So if you don't have any idea of where are good points or potentially good points, you have to spread your points to the entire space. So there are methods like space filling algorithms like Latin hypercube, methods that comes from the statistics literature. You can look into, if you specify 100 points, it will give you a very nice distributed spread with Latin hypercube, or there are modifications to Latin hypercube that you can use. So these are some things we always use as a starting initial population. So we start with that because we have no other knowledge. But in most practical problems, we have knowledge, okay? And we try to use that to put our initial population at potentially good points, okay? When you're designing something, it's most likely you're not doing it for the first time. Somebody has done it, some other competitors have it. So you can look at how the solutions may look like and put a bound around each of these variables and say that this is where I'm going to put my initial solutions. What you also do is, if like in auto industries, for example, they have lots of models, right? Lots of different cars. So if they're doing a particular engine, you take the engine from 5 different successful cars, extract all the variables. So they will be like, if you have 10 variables, in a 10-dimensional space, you have 5 points now. So now you can use a crossover between these 5 points and mutation around them to create your initial population. So you're saying, these 5 successful designs, I'm going to change a little bit around them and start with my initial population. Because with my new design, new parameters, maybe a solution close to it is going to be the optimum. So why start elsewhere? So when you have a large size problems, these kinds of customizations become very, very useful. You may not end up with the global with that kind of idea because you're leaving out some options. But if you want to solve it with 100 evaluations, nobody is expecting you to to deliver a global optima. All they are expecting is, have you got anything better than what we have now, or have you got a reasonable solution, if they don't have a solution from before, to the problem they gave you? And what is the reasonable? And all this is at their place. So all you're trying to do is, with 100 points, you're trying to get something that looks converged, that looks better, that looks reasonable. Where is the global optima? Nobody knows in many of these problems. But in numerical problems, where we have lots of, we can see the function, we can differentiate them, we can actually use weeks of computation to find out where actually the optimum is. We could do a lot of comparisons, see how my algorithm did with another algorithm and all that stuff, how I should initialize at all places. I think both research has their place. One is more applied, where research is the main issue, solving the problem is the main issue. On the other hand, the academic one, research is the main issue, trying to see, have you able to come up with some generic conclusions of these problems compared to the existing algorithms. Problem solving is not that issue. So if you try to use any customization, most likely your paper will be rejected if you are sending it to a academic journal. But fortunately, there are lots of other journals which are more applied. Let me advertise Oliver's Engineering Optimization Journal is one such. We've been sending there. So they really take applied solutions there. And you can use a custom algorithm there if you want to show that that algorithm is the way to solve the problem and describe it in a very generic way what that is. So people are looking for the ideas from you. It's not that how you solve that particular problem, because they may not be interested in that problem, but they're trying to see the philosophy of what you've done. Right? So there are some such journals. So there is a place. And I think the best thing would be for you to do a balance of both academic as well as this applied. So you are kind of doing both and knowing the difference. Unfortunately, there is a gap, okay, between the two. One doesn't help the other too much. But that's how the practice and academic research is currently. Okay.
¿Alguna otra pregunta?
Over here at the front. You can tell, I can then tell the question again.
How different objective function handlers affect the convergence? Is there any study? And thinking the objective function handler as the analog of constraint, is there any combination to be or not to be greedy?
Can you repeat the first part of your question again? What?
How different objective function handler affect the convergence?
Objective function what?
Handler.
I am not getting that word.
Handler.
Handle. Objective function handling.
Yeah.
Okay. So you're talking about multiple objectives. Okay. So we have the standard ways of non-domination check and the crowding distance as some kind of niching to say I want to have a diverse set of points. So that's really the way we handle different objectives. Normalization is a big thing that's needed, but in evolutionary methods, normalization is piece of cake because you have a population. So you have 50 points. Objective-wise, you can find the minimum, maximum of each of the objectives and make them to 0 to 1, 0 to 1. Now you can compute distance between objectives. Although one objective may be in the order of thousands, the other objective may be on the order of 0.1, 0.2. But when you normalize, based on their min-max, they are all between 0 and 1. So you can compute distance between them in the objective space and all that. So this kind of objective handling is we've been doing for different kinds of industry problems without any difficulty. But your second part is objective and constraint handling. That's a more difficult question. And how do you handle the constraints with objectives? Because the traditional way, people try to put them in one platform saying this is a penalty function, where you take the constraint violation, multiply with the penalty parameter, add it to the objective function, and that's how you handle constraints with objectives. But penalty parameter is an important parameter now. So in our constraint handling, we try to avoid having a new penalty parameter by doing, again, some careful comparisons. Like, remember the tournament selection where I said 2 points needs to be compared to choose which one is better. If the 2 points you are comparing are both infeasible, we look at which one is less infeasible. Like in one of the steel casting one I showed you. If one is feasible, the other is infeasible, I always choose the feasible. If both are feasible, I choose the one with the better objective value. So you could do this kind of hierarchy between feasibility and infeasible solutions. And that's how you handle, instead of combining them into one. Because when you try to combine them into one metric, the constraint violation and the objective function, you need a parameter to make a balance. Otherwise, if your constraint violation is very small, this just in the noise of the objective value. Or if the objective function value is very small, you are not treating the objective function at all. So those are not good ideas. The good ideas are if somehow you can make a hierarchy in the comparison. And so I've done that for single objective constraint handling as well as multi-objective. The single objective paper was out in 2000. Multi-objective was with NSGA2, so from 2002. So since then, people have been using that as a default method. Okay, but this is a very good question. Yeah?
Hi, thank you for your great presentation.
Thank you.
I have a question more from the machine learning perspective. Now in these deep neural networks, we have to train a ton of parameters.
Yes.
And we always use this stochastic gradient descent.
For weights.
And in which cases you think that we can apply genetic algorithms?
Good question.
Because now these networks are deeper and deeper,
deeper and deeper.
and we have the problem of vanishing gradient.
Yes.
So where we
Yeah,
can apply that?
it's really not known how much every weight contributes to the final outcome. Really, it's such a deep thing. We have not even trying to optimize for the weights using evolutionary methods. That's like too many weights, okay? So we rely a stochastic gradient approach for the weight we actually get from the Python routines that are available for doing this. What we are concentrating on is the architecture search, because you also need a good architecture, because I think remember I talked about the bi-level? In deep neural net, there's actually a bi-level problem, and we are treating it that way. Upper level is the architecture, the variable is the architecture. Lower level is, now that the architecture is fixed, what are the weights? So lower level problem, we are not doing anything with evolutionary. Okay, it's a standard method of the weight learning with backpropagation. The upper level, the architecture search, is where we are implementing an SGA2 with these two objectives. And that seems to be working very, very well in this two-level manner. So I think yesterday I was talking to a friend, and he was also telling that that's really the way to go in the deep neural net, is concentrate using evolutionary computing for architecture search, not for the weights, because there are, first of all, too many, and also people doesn't at this point know what's the sensitivity of them to the final output. We've done some study that way. What my student did is we got a very good architecture with the weights learned using the optimization process. We just do it 3 levels of weights, -1, 0, or 1, depending on the value. We just get it down to this 3 level. The performance doesn't change much, just slightly degrades. So if you don't have all the gradations of the weights, just get into this 3 level, -1, 0, or 1, you have almost a similar performance. But if you change the architecture, then it's a completely bad solution. So I think the weight searching is not that important in a deep neural net search. It's the architecture which is most, and that's where the evolutionary computing again have a lot of role to play. Okay?
Una pregunta.
All right. Thank you very much.
Bueno, les voy a pedir un aplauso para esta excelente plática.
Thank you.
Me voy a permitir entregarle un reconocimiento al doctor por su presentación. This is to certify that Dr. Kalyan Modev presented the keynote conference titled Evolutionary Computing for Efficient Solution of Practical Problems during the 15th International Congress Technological Trends in Computing, held in Mexico City, October 16 to 18, 2018. Thank you very much, Dr. Dev. And I give for you. Thank you, sir. Ahora, para continuar con nuestro programa, vamos a tener un receso de 10 minutos en lo que se prepara la siguiente conferencia. Si ustedes gustan pasar, hay bocaditos, hay bebidas. Y continuamos con el doctor Efrén Mesura, por favor. Ahora, antes de que se vayan, les recuerdo que mañana continúan las actividades del Congreso y vamos a tener 2 talleres en las instalaciones del CIDETEC. Entonces están cordialmente invitados a ellos. Uno es sobre modelado y el otro es sobre paradigmas de la física. Muchas gracias.
¿Este cómo lo apago? ¿O solito se pueden stand-by? ¿De aquí?
Hey y'all, listen. Last night, I was out with some of the cats in the band, and we were having a good time. You know, we had this little blackjack game going on, you know what I mean? And I somehow got lucky. And every time I tried to leave, they kept yelling at me. You know, they want to get their money back. So I stayed there until I had all of it. And you know, friend, I was so excited. I just left there and I started whistling to myself. Oh man, I'm thinking when I get home, my woman gonna be so glad to see me. I know she gonna open the door and she gonna open her arms, and I know she gonna open. I was wrong as hell. I tell you right now, she was waiting on me all right in the middle of the living room floor. I couldn't believe what was happening. The woman went crazy. She stopped yelling and screaming at me, talking about
Sus intereses de investigación son el diseño y estudio de algoritmos mejorados en la naturaleza aplicados a resolver problemas de optimización. Sobre estos temas ha publicado más de 145 artículos en revistas y conferencias especializadas, con arbitraje estricto, un libro editado con editorial internacional, 11 capítulos del libro y varios reportes técnicos. De su trabajo se reportan más de 5.800 citas en el sitio de Google Scholar. El doctor Mesura Montes es miembro nivel 2, área 7 del Sistema Nacional de Investigadores, el SNI, y también es miembro regular de la Academia Mexicana de Ciencias, miembro regular de la Academia Mexicana de Computación y miembro de la Red CONACYT de Inteligencia Computacional Aplicada. Además, es miembro del Comité Técnico de Computación Evolutiva de la IEEE Computational Intelligence Society y miembro del Comité Técnico de Cómputo Suave de la IEEE Systems, Man and Cybernetics Society. Es además el fundador de la Fuerza de Tareas sobre Optimización con Restricciones usando algoritmos inspirados en la naturaleza de la IEEE Computational Intelligence Society y es miembro regular del Machine Intelligence Research Labs, MIR Labs. Por si no fuera suficiente, es miembro de los comités editoriales de la revista Swarm and Evolutionary Computation, Complex and Intelligent Systems, International Journal of Dynamics and Control y del Journal of Optimization. Fue además miembro de los comités editoriales de las revistas Computational Optimization and Applications and Soft Computing. Es revisor para más de 20 revistas internacionales especializadas, incluyendo el IEEE Transaction on Evolutionary Computation y el IEEE Transactions on Cybernetics. Para más datos sobre su biografía, les aconsejo consultar las páginas de las ligas de Scopus y de Google Scholar, donde van a encontrar aún más de su trabajo, su extenso trabajo. Doctor, por favor.
Muchas gracias. Muchas gracias. Buenas tardes. Good afternoon, everybody. Thank you for the nice presentation. I want, first of all, to thank the organizing committee for all the support to be here. Thank you, Kalian, for accepting this invitation. It's an honor to share this audience with you. Thank you. Okay, this talk is about a particular niche of application for evolutionary computing, and it has raised a lot of attention nowadays because of the emergence of data. So, and it's called evolutionary data mining. So the idea is to show you some experiences that we have with colleagues working on data mining, and this positive combination of evolutionary algorithms with the problems that they're trying to solve in order to generate models based on data. I will briefly talk about my institution. After that, I will talk very briefly, because Kalian has nicely introduced evolutionary algorithms, about the evolutionary computing. After that, I will talk about data mining, and I will talk about the knowledge discovery in data, which is not a very popular name as data mining, but we will briefly detail how is data mined inserted within KDD. Then I will show you some works that we have been doing when combining evolutionary computing in data mining, and the future trends, a list of future trends, which are not future but present trends. Okay, the University of Veracruz, where I come from, is this is the state of Veracruz, which is a very large state, covering most of the part of Gulf of Mexico. And Jalapa is located in the middle of the state. It's a mountain area, but it is close to the coast, so we have a very nice weather all year. It rains a lot, like today, so I'm used to this type of days. And this is Jalapa, which is located in the mountains, and we have a very nice hill in the middle of the city, which is called Cerro de Macultepetl. And we have a very nice recent sculpture like this one, which is called the Araucaria. Araucaria is a type of tree that is very popular in Jalapa. And the artist put the X of Jalapa and the V of Veracruz to form this sculpture that represents Jalapa, and it is located in a very crowded cross avenue in Jalapa. And in downtown Jalapa is located the Artificial Intelligence Research Center of the University of Veracruz. We have a very nice view when there is no cloud in the skies. We can see the Pico de Orizaba, which is the highest mountain in Mexico. And within the Artificial Intelligence Research Center, we have two graduate programs. The first one is a Master on Artificial Intelligence. We've started in 1994, so we have now 25 years of artificial intelligence in Jalapa. And I think the colleagues that started this master degree 20 years ago were visionary, because today everybody talks about artificial intelligence, but it was not the case 25 years before. So we are glad that we have the oldest artificial intelligence program in Mexico located in Jalapa. And this is the youngest brother of the Masters of Artificial Intelligence, the PhD, which started in 2012. And fortunately, we have a lot of interest of students trying to specialize on artificial intelligence topics. Artificial intelligence is a very broad area, so we are grouped in three research groups, and in this way you can understand what type of specific topics are treated in the Artificial Intelligence Research Center. The first one, I belong to this one, Artificial Intelligence Research and Applications. We are focused mainly on computational intelligence techniques, and we try to apply them to real-world situations. There are a group of colleagues working on robotics, and they try to apply them to particular problems. And finally, there is a group of physicists who work on artificial intelligence. They apply particular data mining techniques to one area within physics, which is called econophysics, time series processing and stuff like that. So this is the area that is treated in the Artificial Intelligence Research Center. Okay, so let's briefly talk about evolutionary computing. Evolutionary algorithms are based on the emulation of the evolution of a species, the survival of the fittest, and they are good optimizers. And a little bit later, we will talk about why optimization is useful on data processing. This is a graphic explanation of the evolutionary algorithm. We have a set of solutions to a given problem, and we select the best one based on a parent selection technique. After that, we allow them to recombine, to reproduce and generate new solutions. After we generate new solutions, we have the offspring population. So our population size has increased. So the last part of the evolutionary algorithm is a replacement process to cut the size of the population to start with a similar population size for the next iteration. So I need you to keep this image, this slide in your mind, because we will need it later in the talk, and because we will see how this model can be applied to different situations in data mining. There are different evolutionary algorithms. The most popular is the genetic algorithm from John Holland. With David Goldberg books, which has a broad an important projection to different areas. But there are also the evolution strategies for the German guys, which are very good algorithms to solve numerical optimization problems. Evolutionary programming from Lorenz Vogel. And more recently, genetic programming from John Cosa, which allows to represent solutions based on trees, not just on linear representation. And more recently, the differential evolution algorithm, which is a very good and simple approach to solve numerical optimization problems. And all of them are very solid algorithms. There is a lot of specialized literature where you can consult the details. There is a little brother of evolutionary algorithms, and in recent times it has drawn a lot of attention in the area, which is swarm intelligence. Here, the biological metaphor, which is based of these algorithms, is how simple organisms like bacteria or insects can cooperate to solve a problem in a jointly way, not just in a single way, but with a very basic form of communication. And based on this communication, emerges a very interesting type of somehow called intelligence. And that's the name, swarm intelligence. In this case, I take the example from the bees, which is an algorithm was proposed by Caraboga some years ago. In this case, he observed that bees can explore the area near the nest, the hive, and get some experience about the type of flower that they are exploring. They are able to taste the nectar flavor. They know where is this flower located, and they go back to the hive to communicate to other bees this experience. There is an area within the hive where the bees can communicate, and bees can communicate. Do you know how can bees communicate each other? Does somebody know? No? It's something that I do in a very bad way, which is dancing. They dance. So they dance and they communicate with that dancing all the information about the flower that they visited. So they try to convince some bees in this dancing area to join them to recollect that nectar. So at the end, this foraging process is optimized. So these are very good metaphors to be implemented in a computer and try to use them to solve a problem. Okay? So I take the bees because this is an algorithm that has survived for some years and it has some interesting applications. However, there is an emergence of a lot of algorithms based on the swarm intelligence that have been proposed, and they are some of them are somehow successful, others are not so, but and we need to be careful about what type of algorithm we are choosing to solve a problem, because some of them are very well detailed in the literature, some of them not. So it is important to know which algorithm is solid in the literature to select it to solve a particular problem. Okay, so this is the part of evolutionary algorithms, a little bit of swarm intelligence, but let's talk about data mining. Data has been always been available, but not so in the way that we have access nowadays. But data has been always processed to generate some charts, some statistics about the data that we have available. And that's important because the human can take decisions based on these statistics or charts generated from data. And this is a very old activity. What has changed? Okay, today we have data. In fact, we have a lot of data available. But now, we are trying to generate not just some statistics about data. We are trying to generate models about data. We are trying to generate knowledge about data. And we are generating models in such a way that the computer can help me for the decision-making process. So that's the idea. The goal is the same, but there are differences with respect to the traditional way to deal with data. As I mentioned before, there is a lot of talking about data mining. However, as you can see in this graph, which is the whole process called knowledge discovery in databases, KDD, data mining is just one part of the process. We have the data here, we have the knowledge there. So we need to pass for different steps to get that knowledge available. First, we have data. We have to select the important data, the useful data. After that, we need to pre-process data to transform it. And then we can think on data mining. After that, we need to do some post-processing for the results. And then we can get the knowledge available. So evolutionary data mining is just one part. So even the talk is about data mining, it is important to keep in mind that we are really talking about knowledge discovery in databases, because I will talk briefly about these other aspects, which are very important. And these are the experiences. Okay, I go back to my KDD graphic representation. And okay, we think on data mining. But as you can see, we need to do some stuff before. Sorry. When I do data mining, and this is like the most fancy part of the data processing, we can think on different techniques. For example, artificial neural networks. And if you want to be very updated, we can think on deep learning. But it is the same. We can think on decision trees. And we can think on Bayesian networks. And we can think on support vector machines. And it is the fancy stuff of data mining. And there are other approaches. And an important part of the specialized literature is focused on this type of techniques. However, data mining, the computer is very fuzzy. Computer is not as good as us to treat with data. The computer needs data in the way that the computer needs it. Otherwise, the results cannot be as good as expected. So I'm talking about then this transformation part. Otherwise, we can fail here. I think a very important part of research is devoted to work with data mining, but what about transformation of data? Mostly in real-world problems. So, one part of important part of this pre-processing is data discretization. So we need to move from continuous to discrete data, because computers prefer discrete than continuous data. That's the way it is. But without losing information. So what we have here an optimization problem. The message here of this talk, I hope, is that underneath data mining, knowledge discovering data, data analysis, and all those fancy techniques nowadays, underneath all of these, there are optimization problems. So if you want to work with data, you need to know optimization. Otherwise, maybe the knowledge that you are generating is not the one that reflects the data that you are taking. So that's the message of this talk. Okay, so I have numerical data, and I want to, without losing information, I want to generate some discrete information which will be easier to handle for the data mining process. The good news is that as we know evolutionary computing, we can evolve discretization options. And as you can see, that's the reason that I asked you to remember the slide of the evolutionary algorithm. The process is a very general one to deal with different problems within knowledge discovering data. The key here is that we can generate different options to discretize data, and at the end I will get a very good one. And the interesting thing is I can compare the solutions provided by the evolutionary algorithm with respect to traditional discretization techniques. And the evolutionary algorithm is able to provide a very suitable competitive solution with the same model that I explained you with the horses. What's the difference here? It is in red. I can decide what is the criterion to discretize data. In this case, we chose classification rate. And that's okay. But I can use the one I need. So I can adapt the evolutionary algorithm to different situations, as Kalian mentioned, that it is important when you are trying to solve real-world problems. Otherwise, you are trying to a very fixed algorithm. It is hard to deal with different situations. So in this case, we decided to use classification rate. We are using the data mining process as an objective function for data discretization. That's nice. And we can also discretize not just a traditional data set, for example, but what about temporal data sets? When I have time series data sets and I need to generate a discrete, which is just this part of the time series, which represent the behavior of the time series. And this type of representation is more suitable for the computer than this one. But remember, we don't have to lose information. Again, an optimization problem. And good news, the process is exactly the same. And in this case, again in red, we can decide what do we need to optimize. Okay, we need a classification rate, but in this case, we are also considering the compression rate. So we are talking about a multi-objective optimization problem. And there are very good evolutionary algorithms that solve multi-objective optimization problems. But the process is the same. And again, we need to compare with traditional time series discretization techniques, and we are getting very good results. Another very typical problem with data, just to mention a case in health problems. It is very common to have imbalanced data. You have many cases of people with some disease, but a few cases with people which are healthy. So the computer is not magic. If you give this imbalanced data to the computer, it will be very good to detect people with some illness, but it would fail to detect people which is healthy. So how can we deal with that? With the same process. So we have a majority, a minority class, So the model can be incorrect. So now we have different ways to generate data to try to balance that minority class, for example, but with the same process. But again, what do you see in red? Now we can have a multi-objective optimization problem where the classification rate is important, but not just the classification rate. We can think on the distribution similarity of the new generated data with respect to the original data. So I'm trying to guarantee that the new data that I'm trying to generate is the same with respect to the original data. Feature selection. What happens when I have a lot of variables in my data sets? It is common in bioinformatics. A lot of variables, a few cases. How can we deal with that? Well, feature selection. And there are different feature selection techniques, again. But evolutionary algorithms are able to provide very interesting solutions. And we simplify the process. So, for example, here I have 4 variables. Maybe I can omit the first and the third, and we keep just the second and the fourth. And based just on these 2 variables, I can model the process. In this case, for example, we worked with the Kinect sensor because we were trying to detect elder people living alone when they fell down. So we tried to detect this fell down. So we wanted to eliminate the points in this skeleton representation of a person who are not helpful to detect a fall down. But the process is the same. In this case, we use again the classification rate, and in this way, we can, at the end, tell the machine learning process which are the points needed to detect a fall down. Not only the preprocessing is able to be optimized by evolutionary algorithms. In this case, we are talking with some colleagues working on Bayesian networks, which is a very nice model because it's a graphical model, which helps you to understand the phenomenon that you are trying to understand. So we have a model like this one when you have different variables and you can see the dependence with this variable represented by these arrows. And we have different types and sizes of the Bayesian networks. Again, the process is the same. Now I am using swarm intelligence, but it's the same process. We are trying to generate a very good Bayesian network. I have this example because in this case, some colleagues were very interested on using PSO because they say that this is a very fast algorithm, and in some way, in a practical way, it is. But they were dealing with very huge Bayesian networks because the problem that they are trying to model is based on some environmental aspects. And they have information from satellite images, some research, field research, and tons of data. So the Bayesian network is huge. So they try to optimize this type of model because they want to present this graphical model to the decision making. And the decision maker here is a politician. And a politician don't believe in computers. So we need a very nice model to present, for example, what happened if the government decide to put a road crossing some gardens in the Polytechnico. Which species will be affected? So ¿Pueden darle clic a la imagen, por favor? A cualquiera de las dos. Gracias. So, this is just a video of a small Bayesian network, but as you can see, the video is running. We are trying to optimize this Bayesian network by using particular measures that the colleagues of that area use, which is called MDL. This is one of the metrics, and the other one is the classification rate. So the evolutionary algorithm can deal with that, and in an automatic way, it can provide you with a very good model. When this collaboration started, the colleagues from the this environmental area were generating those Bayesian networks handcrafted. Now they have a tool based on their data to automatically generate a very good Bayesian network. And they can compare their designs with respect to the ones that the computer is giving. So that's a very good tool to improve the decision-making process. Okay, can you stop and go back to the slide, please? No, that is not necessary. It's the same. It's a bigger Bayesian network, but the process is the same. Thank you. Okay. What about model selection? What is model selection? Why not optimizing the whole process? Do you remember this image? We were dealing with this part and this part, just. Why not asking the evolutionary algorithm to give me all the suggestions for the process? And it is called model selection, full model selection. So this is a very interesting optimization problem, because at the end, the computer will give me how to select data, how to pre-process data, with the particular technique, the transformation, the data mining, and the post-processing technique for a particular data set. In this case, we deal with a multi-objective problem because we want a model which is very competitive based on classification rate, for example. But we also want a model which is not very complex. So there's a trade-off between these two objectives. And more importantly, and Kalian talked about that, once I get different full model options, we need to choose the best one, which is preference selection. And in this case, we were guided by the colleagues working on full model selection based on the solution that they needed. And most of them, in the experiment that we made, were located in the knee of the Pareto front. But as you can see, the process is the same. There is a lot of research work on supervised learning. But what about unsupervised learning? Most of the cases, you assume that your data is labeled. You know for which one of your data, you know the class. But if you don't know the class, you need to deal with unsupervised learning. So we work, in this case, with multi-objective evolutionary clustering, which is a very interesting idea. We work based on a multi-objective based approach, which does not require the number of clusters in advance. And based on that, you can have different grouping options for your data. This is the data. These are the different options for grouping, and you generate a Pareto front. And after that, you can use some measures from the clustering area to select the best clustering approach for your data. In this case, for example, we guided the multi-objective search based on intra and inter-cluster distance. But you can add the objectives that you need based on the type of grouping that you are trying to get in your process. Again, flexibility. Okay. What about the future trends? And this is my personal point of view. Any critics? You can share with me at the end of the talk. What is next? What is now? I consider the full model selection as a very viable alternative, a very heavy to process, but we need the computer based on evolutionary algorithms to give me some options based on the data that I am trying to process. Everybody talks about deep learning, but if you work with deep learning, you need a lot of data to train that huge neural network. It is not the case in all domains. What happens if you have just a few data available? Why not researching about learning by small data sets, but a good learning process? A few weeks ago, we have a meeting with some colleagues from France, and they were very interested in learning by small data sets. And it is very common to have a particular real-world problem when you have just a few data available. What about explainability? Deep learning, it's good. But if you ask the deep neural network how the decision was taken, it cannot answer. Why? And for example, if society is thinking on artificial intelligence as a viable option to solve complex problems, we need the computer to tell us how the decision making is constructed within the machine. So, explainability. We need models that let you know how the decision was made. Otherwise, it's obscure. It's like magic. And it is not desirable in many domains. For example, in medical domain. If you are feeling ill and you go to the computer and the computer says, you have an illness. Why you have an illness? But why? Tell me why you have an illness. That's the only thing that, for example, a deep neural network can answer. We need to think on the other learning areas which are a little bit forgotten. On supervised learning, I mentioned about that. But what about reinforcement learning? It draws my attention that in the recent version of the two important conferences of an evolutionary algorithm, CEC and Gecko, there have been special session workshops interested on reinforcement learning. They call them evolutionary machine learning. And they are using mainly evolution strategies to solve some reinforcement learning problem that they are trying to compare in huge instances with traditional techniques like Q-learning, which are very expensive when the problem grows. So people is interested on evolutionary algorithms to deal with this type of problems. And this is it. Thank you.
Vamos a continuar con las preguntas. ¿Alguien desea hacer alguna pregunta? ¿Preguntas?
Hi, thank you for your presentation. And I have a question about how do we measure if the optimization is failing or is stuck in a local optima, or maybe the classification method is stuck because the classification technique is not capable of solving the problem. So how do you know when is the optimization and when is the classification?
Okay, it is important to mention that these evolutionary algorithm techniques are always the second option. When you come to evolutionary algorithms, you already have been tested traditional techniques for your particular problem. So if you want to know how good is your evolutionary approach, you already have the traditional technique to compare. This is a first choice for comparison purposes. In the case of supervised learning, you have the advantage if you are using classification rate, because you have a very clear value. And in some real world problems, the experts tell you, I need 90% or above to consider your model as good. I have one of my former students, PhD student, which is now working in Australia, and she's working in a spin-off from University of New South Wales. And her work is based on the classification rate that her models can reach based on data. So that's the way you can know if your solution is good. You need information for the particular data set from the expert, and you can have some limit to surpass and see if your approach is a good one. It is not the case in unsupervised learning. It is kind of tricky when you don't have the guide of a class.
¿Alguna otra pregunta?
Thank you for your great presentation. If we concentrate on using evolutionary algorithms for these kind of machine learning problems, which are classification or feature selection and some of these, when we apply them to optimization problems, we have some known algorithms like point-based, gradient-based, all these methods that you can compare and say how well they're doing. In these kinds of problems, is it that the people are comparing with some existing methods? If yes, then are they standard algorithms that are accepted, and how is these evolutionary methods different from those results?
Yes, the first answer is yes. There are well-established methods. Actually, unlike evolutionary algorithms area, data mining, KDD, machine learning area has very established and well-known software available, like Weka, for example, or those that's library from Python, MATLAB, etc. And you have all those methods already available in those languages. So it is very easy to compare. My concern is that, for example, there are many people that take that software and say, okay, I will use random forest technique to generate my decision trees. And they use Weka. This is my data set, and this just some clicks, and they get the model. But the model was generated by a greedy search, for example. So are you sure that this tree that you are generating is the best one, the best possible one that you can generate from your data? You don't know, and you take that for granted. So that's my point. You need most robust optimization technique underneath, and try to compare with those well-established and accessible solutions. And what we are discovering is that evolutionary algorithms are able to improve the quality of those models, because most of them are based on very basic search techniques. And the student or the expert are not aware that they can change, for example, the parameters in that type of software. But they don't do that. And they don't even think on trying to use other more robust optimization techniques. That's my point. That's the idea that I'm trying to push to this area.
Anyone else? No? Bueno, nuevamente un aplauso para la presentación.
Muchas gracias. Thank you.
Le agradezco al doctor Efren su espléndida presentación y bueno, procedo a entregarle su constancia. Nuevamente this is to certify that Dr. Efren Mesura Montes presented the keynote conference titled Evolutionary Data Mining, Lesson Learned and Future Trends during the 15th International Congress Technological Trends in Computing, held in Mexico City, October 16 to 18, 2019. Thank you very much, Doctor. And I give for you. Bueno, nuevamente agradezco a las autoridades, tanto de la UPDCE como del CGFIE, el uso de este espléndido auditorio, de las instalaciones en general, y los invito a que participen en los talleres del día de mañana. Tenemos 2 talleres, permítanme comentarles cuáles son los temas y los horarios. Un segundo. Oh my God. Bueno, el primer taller comienza a las 10 de la mañana, sobre modelado dinámico, y el segundo taller comienza a las 12. Sí, a las 12. Entonces es sobre paradigmas de física. Muy interesante, por cierto. Están cordialmente invitados y muchas gracias por su atención y su presencia. Que tengan una excelente tarde.